Hello, thank you for watching this presentation. Our team will be presenting on the power split hybrid electric vehicle. Made up of 5 people in our team, we have Ji-Sung Lee, we have Mark Postonek, we have Alamin Salah, we have Rashawn Childers, and then we have myself, Edmund Nar. In this presentation, we will talk about the motivation, we'll talk about the hybrid electric vehicle in detail, then we'll go into the problem formulation, which is the MPC model. And then from there, we will go into the nonlinear MPC model and the linear MPC model, after which we will walk you through the simulations and then our conclusions.
Hello, my name is Rashawn Childers. I'll be going over the motivation for our project and the type of system we decided to study. Over the last few decades, we've seen a revolution in the auto industry with the rise of electric and hybrid electric vehicles. There's been steep competition between conventional vehicles and hybrid electric vehicles, with hybrid electric being the most efficient of the three. In our project, we decided to look at a power split hybrid electric vehicle configuration. With this higher efficiency also comes higher complexity and energy management. So we decided to study how different settings in MPC affect the energy management of the model. Here you can see a figure of our power split system. It consists of two energy sources being the engine and battery. Here you can see there's an electrical mechanical power split with the engine sending mechanical energy to the planetary gear set, which sends mechanical energy to the torque coupler, and both of which can send and receive mechanical energy to the generators and motors, which convert the mechanical energy into electrical energy, which is stored in the battery. This is efficient because we are storing wasted energy from braking, which would otherwise be dissipated into the atmosphere.
So for our MPC model, we took the following parameters. First, the state variable is defined by our battery's state of charge. Secondly, the control variable is defined by our two variables, the torque and the speed of the engine. Another parameter to take into account is the measured disturbance, defined by the torque demanded by the driver of the vehicle and its velocity v. Finally, we measure the fuel flow rate, the power of the generator and its speed, and eventually the motor and generator torques. Finally, our computational time depends on the sampling time, number of time periods per iteration, and our model type.
My name is Pustilnik Mark. On slide 7, we can see the mathematical problem formulation for the MPC optimization. So the cost function tries to minimize the amount of fuel used, meaning minimize the use of the petrol engine, and bring the state of charge of the battery to some reference value. The formulation on the left is the full dynamics formulation of the problem, and it includes the dynamics of the electrical motor and the petrol engine. And on the right is the same formulation but reduced to hold only the decision variables of the MPC.
Hi, I'm Jisun and I will briefly go over the MPC model we used and the simulation results for the nonlinear MPC model. In the nonlinear MPC model, we iteratively solve an period energy management problem given as follows. Additional to the cost function given in Borhan's paper, we added quadratic cost of the speed and torque of the engine and a fixed cost S that occurs whenever the engine is on. A binary variable z engine is also defined to assign 0 to the speed and torque of the engine when it is off, and also account the fixed cost of the engine turned on. As the Groby solver we used, and also most of the commercial solvers, cannot formulate interpolation constraints of more than one variable, we approximate 3 empirical maps with 2 decision variables with polynomial functions. Then for the linear MPC, we first reduced the problem dimension by projecting out some auxiliary variables and linearized the simplified formulation using partial derivatives. For the simulation, the parameter values are chosen as follows. Then we simulated the nonlinear and linear MPC with different MPC time horizon, which is 5, 10, and 12, and the sampling time 0.8, 1.0, and 1.2 with total simulation duration of 100 seconds. For the nonlinear MPC model, all instances were solved within the time limit set as the sampling time. For the linearized MPC, however, it failed to obtain feasible control for the simulation duration as the formulation was not the exact one. Let's just see the simulation results for the nonlinear MPC. First, the state of the charge of battery seems to be following very similar flow for all instances. However, the fuel rate highly depends on the number of horizon of MPC and also the sampling time matters. For the current, it also seems to be very similar in most of the instances, which was expected as SOC is a function of current. Comparing the computational time, it reduces as n decreases, which is obvious, and also decreases as the sampling time increases. The final SOC is almost the same for all instances as we have seen in the graph. However, the total cost and the average fuel rate also increases as n increases, which is not what we expected, as when the time horizon we consider in each period increases, we expect that it would do better control with less cost.
To conclude our presentation, we were able to formulate the energy management of the power split hybrid vehicle and run simulation with different time horizons and sampling times by using two types models: the nonlinear MPC with discretization and polynomial approximation, and the linear MPC model using the gradient approach. However, the performance of our model depends highly on the data in order to give us accurate results. Besides, the linear MPC model couldn't reach the desired output for the simulation time horizon of 100 seconds. And finally, we obtained some unexpected results for the nonlinear model that needed additional work to analyze. Thank you for your time.